Okay, this is lesson 4.1, solving polynomial equations. When we solve a polynomial equation, what it means is it means to determine which values of x make the equation true. We talked in previous classes about what roots are. Roots are the values of x that make an equation true. Therefore, when we solve an equation, we're determining the roots of that equation. When we're looking at polynomial equations, and we're determining the roots, if the polynomial function is factorable, the strategy that we need to use is to factor. If a polynomial function is not factorable and you want to determine the roots, the only strategy we have is graphing technology, or Desmos would be the technology you're probably using. Sometimes you're left with a unfactorable quadratic term that you can determine roots for using the quadratic formula, and we would need to apply that strategy when possible. So, if possible, factor. If you're left with a quadratic that's not factorable, you can use the quadratic formula. And if you're left with a polynomial that's above degree 2, so like a degree 3 or degree 4, and you can't factor it using the factor theorem, you have to use graphing technology in order to find the roots. So we're going to look at 4 different examples that pretty much cover the 4 scenarios that we might encounter when solving a polynomial equation. Our first example is a factorable degree 3 polynomial. So that means we're going to have real roots that we can find by factoring. So if we have a degree 3 polynomial, we would want to use the factor theorem in order to find a root that we can do some polynomial division on our degree 3 polynomial to end up with a quadratic, and then factor the quadratic to end up with our other 2 roots. That would be the strategy, and we've already done some of that in the past unit. What's new here is that we've turned it into an equation set equal to 0, and we're asked to solve. Before in Unit 3, we were given a polynomial that looked like this, and it might have said f of x equals, and you were asked to graph it. So the strategy to graph it would be to find the x-intercepts. Well, the x-intercepts are just when y equals 0, so it's when that function equals 0. So it looks like that, and what we're doing then is we're actually just solving. So we've kind of already done this already, but let's try it again and see what it means when we look for our real roots and what that means in terms of where they end up on a graph. So let's solve this. To solve it, we want to factor. And to factor, we need to think of roots of 6 that we can test to see if we get a 0 remainder, which would mean that they're a root. So the factors of 6, plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. And if we test each of those in for x, a few of them, or maybe just a couple, will give us a remainder of 0. So I'm going to try 1 in my head, and nope, it doesn't work. I'm going to try negative 1, and nope, negative 1 doesn't work either. So I'll try 2, and 2 does work. So if we try x equals 2, we can say that our function, let's call this f of x, f at 2 equals 0, therefore x minus 2 is a factor. So what am I doing here? Well, I'm plugging 2 into the function and seeing if it gives us 0, and only one that I started trying 1 and negative 1, 2 did work, therefore x minus 2 is a factor. If I tried minus 2 and it would work, well then x plus 2 would be a factor. But in this case, x minus 2 is a factor, so our root is 2, so I'll do some synthetic division here. I'm going to take my root 2, and I'm going to divide it into 2x cubed minus 9x squared plus 7x plus 6. So for my synthetic, you bring down the first 2, multiply, we get 4, add down the column, you get negative 5, multiply, we get negative 10, add down the column, you get negative 3, multiply 2 by negative 3, you get negative 6 with a 0 remainder. which means that we now have a quadratic x squared, 2x squared minus 5x minus 3 as one of our factors, and our original factor was x minus 2. So now, to continue factoring, we just need to factor this quadratic. So now we're solving 0 equals, we have the x minus 2 factor already factored, and 2x squared minus 5x minus 3. So this is a complex trinomial, which means we need to use decomposition to factor. And if you remember, to use decomposition, you take a and c, or 2 and negative 3, multiply them. So that means we're looking for numbers that multiply to negative 6 and add to negative 5. Numbers that multiply to negative 6 and add to negative 5 are negative 6 and 1. So we break down our middle term into negative 6x and positive 1x. Then we group and common factor. So we group our first two, and what's common to the first two? 2x, left with x minus 3. What's common to the second pair? Nothing, or we can say 1, and we're left with x minus 3. So what we have here is a common factor of x minus 3. So that's our next factor. And we're left with 2x plus 1. And now we're just solving this equation. And to solve this factored equation, we basically take each of our factor brackets, set it equal to 0, and solve. So we get a root from the first one of x equals 2. From the second one, we get x equals 3. And from the third one, we get x equals negative a half. So part B says, what do these values of x represent? Well, they represent the zeros, because this is set equal to 0. They represent the zeros. Or since we're solving an equation, they represent the roots, zeros or roots. But zeros specifically because it's set equal to 0. To sketch, we have to consider a couple things. We know this is a degree 3. We know the leading coefficient is positive. So that means we're going to start low, end high. We know the y-intercept is 6. And we know 3 x-intercepts. The zeros also represent your x-intercepts. So we have negative 1/2, 2, and 3. So what do we know about each one? Well, each order is 1, so that means we're going to pass through these roots. So we're going to start, change my location of my arrow so it makes the graph a little smoother. We're going to start by going through here. We're going to go up. We're going to pass through our first 0. We're going to bend back up, pass through our third 0, and finish high. And that's as accurate as we would need to graph this. 3 x-intercepts with the appropriate behaviors, and our y-intercept of 6. We have the correct end behaviors, the correct number of turning points, because this is a degree 3 polynomial. So what have we done here? We've solved a degree 3 polynomial by using the factor theorem and then factoring a quadratic. And we took our roots and represented them as x-intercepts on our graph in order to sketch. What happens if the polynomial that we're dealing with has non-real roots? So in this case, I've done some of the factoring work for you. Pretend we had a degree 3 polynomial, and we used the factor theorem, and we found that 3 was one of the roots, and we did some polynomial division, and this is the remaining quadratic that we ended up with. This remaining quadratic, if we use the quadratic formula, isn't factorable and doesn't give us real roots because there ends up being a negative sign underneath the square root. And again, it's not factorable because there's no numbers that multiply to 1 and add to 0. That's correct. So how do we find the roots? Well, we can find complex roots. X minus 3, x squared plus 1 equals 0. We know the root from our first bracket is x equals 3. And if we were to sketch this, that 3 would represent as a x-intercept. If we were to expand this out, we would end up with negative 3 as our y-intercept. So we know our y-intercept. But the question is, where is the rest of the graph? We know because it's a degree 3 with a leading coefficient, degree 3, and then a leading coefficient that's positive. We know that it's going to start low and high, but what happens between? Does it cross again, then come back down, then go back up, or what's going on here? Well, what's going on comes from that second bracket. If we want to solve for the root from that second bracket, we take that bracket and set it equal to 0. And if we start isolating, we find the problem here. We move the 1 over, it becomes negative 1. And then if we want to take the square root, we end up with this problem. You can't take the square root of a negative number. You can, though, if you define it as a complex root. Or we can say that let's let I represent the square root of negative 1. I represents a set of imaginary numbers, and the imaginary number set allows you to find roots that are non-real, but algebraically or mathematically they are valid. So what's the practical use of them? They're algebraically practical, but graphically, on the graphs that we're creating, they don't really show you anything else about the polynomial. So what do I mean by that? Well, if we say let's let I equal the square root of negative 1, then we would get 2 more roots, plus or minus I. And those are non-real complex roots. And what do they look like on the graph? Well, what it means is that you don't have x-intercepts, or you don't have any other x-intercepts. The only x-intercept that we're going to have is at 3. So that means that if the graph is down here, all it can do is do some sort of behavior below the x-axis and then curve up and cross the x-axis at the one spot where it says it does. So that means we have this, and then we could have behavior that looks like this. And that's as specific as we can get. We could bring it up and have it bend back down as long as it doesn't cross the x-axis. We could have it go through and then bend back down and then come back up. And the only way we would actually know what it looks like is if we graphed it using Desmos. So the non-real complex roots don't, all they tell you is that there's no x-intercepts for this part, or represented by this part of the polynomial. So if we wanted an accurate image, we would need to use Desmos. And if you check on Desmos, it does actually look something like this. It stays below the x-axis here, crosses the y-intercept, and then bends back up and goes through the x-axis at the only real x-intercept 3, or sorry, the only real root 3. These non-real or complex roots, again, just tell you that there is no other x-intercepts. But algebraically, we have 2 new roots. So they are roots, but they are not x-intercepts on the graph. Whereas x equals 3 is a root, and the 0.30 is an x-intercept. So the roots and x-intercepts are the same in this case, but different in terms of complex roots. Okay, that's part 1 of our video on solving polynomial equations. Check back in for part 2, where we'll solve 2 different types of polynomial equations.